Right. So let me recall what we have done last week. So we are now in chapter 3. Chapter 3 is about Hilbert spaces and operator on Hilbert spaces. I told you it's a generalization of what you can do on Cn. Or if you don't like Cn, you can think about Rn. The problem with Rn or with real numbers is you don't have solution to all equations. The equation x squared plus 1 has no solution on R. It has two solutions on C. So this is why C is convenient. So we prefer Cn instead of Rn. But if you have no idea about complex numbers, you can still think about real space. And when I do this picture, I'm also thinking about a real space. But in fact, you should think about this as a complex direction, on a third complex direction. I introduced the notion of subspace of a Hilbert space and closed subspace. Closed subspace means it's like R compared to Q. You can take the sequences and they converge inside the subspace and not outside. And examples of subspace or closed subspace, the vector space generated by n vectors, just linear combination, it's a closed subspace. If you take any in this space, any sequence, it will converge inside this space. You cannot go outside. On the other hand, the set of test function or the set of Schwarz function, these are subspaces. You can do addition. You can multiply by a constant. You stay in these two subspaces, but they are not closed. In L2 of Rn, if you take a sequence converging in L2, then most probably you will not stay inside the set of test function or the set of Schwarz function. The limit will be in L2. So they are not closed. Another result, which is quite easy to show, is if you take any subset in H, in the Hilbert space, the set which is orthogonal, so the set of F which are orthogonal to any element of M is a closed subspace. I also introduced the notion of density, which means you can approximate as precisely as you want. And there is this statement which said that the orthocomplement or the orthogonal subspace of M, if M is dense, in H is simply 0. You don't have anything which is orthogonal to a dense subset. I didn't give a very precise definition of a dual, but you should think about take any space like the set of test function, like the set of Schwarz function. The dual is a set of continuous function on this set with value in C. We call it a functional. But the point is what means continuity, you have to be a little bit more precise. But last week I mentioned that if we do it for H, if we look at the set of all functions from H to C which are continuous, you get nothing but H itself. So the dual of H can be identified with H. So the set of with a scalar product. And this result is called Riesz lemma. And it's a very important result for many parts. So this is about the Hilbert space. And then we are thinking about bounded linear operators on H. So what is it? It's something which take an element of H and send it to a new element of H, like a matrix. A matrix take a vector and send it to a vector. If you have an element F in L2, a bounded linear operator takes this F and send it to a new element of this space. We define the norm of, and the set of all bounded linear operators is denoted by B of H. The norm of an element of B of H is given by these three expressions. It's not completely trivial to check that they are equivalent, but indeed, either you take the supremum of the maximal number or the supremum over this expression divided by the norm of F, or you take the infimum over all C, which satisfies this inequality, or this one, which is convenient. What is it? You take the sup over all F in a dense subspace of the Hilbert space. You don't even need to take all elements. You can take all in a dense subset, F of norm 1. The same for G in another dense subset, also G of norm 1, and this scalar product. This gives you also the norm. In fact, this equality is it's a theorem or it's a small result. It's not straightforward.
I cannot get rid of it. I have to start.
This inequality holds for norm. You can just check that the two bounded operators, when you take the norm, you have this inequality. And as I said, keep in mind, this is just a generalization of matrices. You get matrices if the Hilbert space is finite dimensional. I also gave, and I will come back to this, your example of a multiplication operator. This is also an example you should keep in mind for a space of, not of finite dimension, but of dimension infinity. Now, on this set of B of H, you have one important operation, which is taking the adjoint. So for any B in B of H, any bounded linear operators, there exists an adjoint, which satisfy this. It's like for symmetric matrices. Any matrix, there exists a transpose and complex conjugate, which satisfies this. And the properties of this adjoint is it has the same norm. You can get it from this. Then if you take 2 times the adjoint, you are back to B. And if you take the adjoint of a product, it's just the product of the adjoint, but in the reverse order. And finally, we have seen 3 notions of convergences. Always convergences is related to continuities, how you approach something. So we have seen on B of H, you can approach uniformly, which means in norm. You can approach strongly when you apply to a vector, or weakly when you take a scalar product. Okay, I have also written for me, probably the last week, because it's fair to do it the last week, I want to take a picture of everybody. I do it the last week because it forces you to stay if you want to be on the picture. If you are taking the course online, I will also take a picture of you online, and I will add these 2 things. I used to do it during the COVID period. Now we are no more, but since we are recording this course, I can still take a picture. So I will do it on the last week, which is probably the 12th or 14th, something like, of July. All right, any question or remark? So let's continue. Today we are going to finish with bounded operators. And next time I will start and I will discuss unbounded operators. We don't know what it is yet, but I will explain what is unbounded, what is an unbounded operator, because they're very useful. So the first topic is about invertibility. So let me just do a picture. And probably you have seen the notion of injective and surjective already somewhere. So remember, we have a Hilbert space and a second copy of this Hilbert space, and I take a B which is in B of H. So an element of B of H is take a F and it send it to another point BF. Now, I would like to know, there is a direction. I would like to know if I can come back. Is there a way to, if you are here, to come back? And this is a notion of invertibility, and it's quite natural. Of course, you can guess when it will not be possible. If 2 points or 2 elements here are sent to the same point here, you will not be able to come back because you don't know if you have to come back here or if you have to come back here. This is quite natural. So let me define or give a definition. So consider bounded operator B in B of H. B is invertible. This is a definition. If, first I write it very shortly, if K of B is 0. But what does it mean? This K is for kernel So I give a definition. This is equivalent to the set of F in H such that BF is 0. The set of F such that BF is 0 is the kernel. This is the kernel. So maybe I should just write this is the kernel. So the condition is that the set is only the 0 element. So the only element which is sent to 0 is 0. This is a condition. So we say that it's invertible if this kernel is 0. Why is it important? Why does it imply that this doesn't happen? So observation. I don't like to do an observation in the definition, but let me just do it. Observation. If the kernel of B is 0, so it contains only 0, 0 is always there, then for any F1 different from F2, B of F1 is different from B of F2. Can you see why? Not plus. Yes, check. Otherwise, indeed, B of F1 minus F2 would be equal to 0. So it's a proof by contradiction. If they were the same, it means that B of F1 minus F2 would be 0. But if the kernel is 0, it means F1 is equal to F2, which is a contradiction.
I'm sure F2 to be minus F1 would be plus as well.
No. So I don't write the full proof, but there would be a contradiction if the kernel is 0 and if two elements are sent on the same, you get a contradiction. Okay, so it means this situation does not take place. Okay, this is just a parenthesis. So still in the definition, then which means if B is invertible, then then exists a unique B inverse Where is this inverse defined? Be careful. I cannot say that the inverse is taking any element here and send it to this one. No, this is not true, because it could be that you cover, B maps you here, but not here. The image of B could, for example, not reach this part. If all elements of H are sent to the yellow part, then you have no way to go from here to here. So it means B minus 1 is defined from the range of B. I will write again the definition to H. What is the range? It is a set of BF for any F in H. So all the elements which are the image of some F, right? So there exists a B minus 1 from this yellow part to H, such that when you start with B and then take B minus 1 of F, you get F, which means you go from here and come back. You're back to F for any F in H. And there is a second thing. If we start here, I cannot start in the red part. If I start here, I go back, and then I apply F, I apply B, I will come to the same point. So we also have B of B minus 1 of G is G for any G inside the range of F, range of V, sorry, range of V. You can only start from the yellow part because you never reach the red one. So this is a definition of an inverse. You can do it whenever an operator is invertible. Still in the definition, if B is invertible and the range of B is the entire space H, so if the yellow part is everything, then B minus 1, which is now defined from H to H, is a bounded linear operator. So be careful what I'm not claiming that always this B minus 1 is a bounded linear operator. I'm saying if the range of B is H, it is the case. And I will show you why I need to be cautious. So we say in this case, we say that B is a boundedly invertible, or has an inverse in B of H. These are the two expressions. But let me show you why it's not always the case. First, we have a question about this definition. Keep in mind this picture. We start from H. We apply B. We get to the yellow part. Maybe we don't reach the red part. If it is injective or invertible, so if the kernel is 0, we can go back from this yellow part to H and applying B and then B minus 1, you get identity, and applying B minus 1B, you get also identity, but on the range. All right? Yes? It's difficult to speak about the size if the size is infinity, because infinity, I'm not, okay, if everything is finite dimensional, you have no problem and you are back to linear algebra. I know what you have in mind. But if it is infinite dimensional, this can be infinite dimensional, this can be finite or infinite dimensional, everything is possible. You cannot compare to infinity. So be careful about this. Let me state an exercise and also remind you something. Exercise. Remember, I define multiplication operator like this. M is a multiplication. And I will be slightly more precise. Let me be more precise. Take H is L2 of R, phi. Now we know this notation. Oh, let me take even a simpler. Bounded and continuous. So probably I use this notation. A bounded and continuous function. Bounded and continuous. So the nice function on R, bounded and continuous, and set M phi for multiplication operator. There are many notations for multiplication operator. Multiplication operator, it means M index phi on the F evaluated at X is just a multiplication of phi of x, f of x, or any f in H. So remember, it takes a function here, f is here, and you multiply it by something else, by another function. And we have shown last week that because it's bounded, this new function is still in L2, okay? Now, let me take an example. Take phi. I want a bounded and continuous function, so I'm going to take hyperbolic tangent. So maybe it's good to remember how it looks like. The hyperbolic tangent looks like this. It goes to 1, it goes to -1. It's a very nice function. If you haven't seen it, okay, it is this function. So it's a bounded and continuous function, sure. So I can define M of hyperbolic tangent. Okay. What is the inverse of this operator? Can you guess what is it invertible, and what is the inverse? So I will not give you the full answer because it's an exercise, but you can wonder what is care of M phi. And I can already tell you the answer. The answer is going to be 0, but you have to show it. So it means it is invertible. And what is the inverse? M phi -1. Okay, sorry, I'm on this example. So phi is the tangent. M hyperbolic tangent. And what is the inverse? What is the inverse? And is this operator bounded? So you can wonder if this inverse is bounded. It's very good to work on this exercise. It's not difficult, but you have to understand the definition of a multiplication operator and understand what is the inverse. I can already tell you the problem is here because this function goes through 0. Right? I leave it as an exercise. And the answer is no, it's not a bounded. The inverse is not bounded. So you have to check why. Let me just introduce two special operators. The simplest one. Which always exists. The one. Be careful, it's an operator. And what is its action? One apply on F is F. You do nothing. Just one apply to F is F itself. You can check it's a bounded operator. It has no kernel. The kernel is 0 because of the definition. The kernel is 0. Okay, it's a trivial kernel. What is the other very simple operator? 0. The 0 operator, what is its action? The 0 operator on any F gives you 0. Be careful, this is not a number 0. This is a 0 of the Hilbert space. And for example, when we deal with function, it is a function which is 0 all the time. It is 0, but it depends. Or it is a 0 vector, so it's a vector 0, 0, 0, 0. So we have these two operators which are always available, always here. Now, in calculus 1, you probably learn this. What is the sum of n from 0 up to infinity? if A is just a real number between -1 and 1, 1 over 1 minus A, if A is smaller than 1. You should know this. If you don't know it, you have to prove it once. Please think about it, how to prove this. This is something we learn in Calculus 1. Okay, I let you think. So there is something similar or quite similar for operators, which is very useful. It's called the Neumann series. Neumann series. Let me state it. If somebody wants to prove this lemma, it's possible. If B is in B of H, a bounded linear operator, and the norm of B is strictly smaller than 1. It should remind you this, strictly smaller than 1. This is indeed a norm, but just on real numbers. Then 1 minus B minus 1 is equal to this infinite sum, n from 0 up to infinity of B power n. What is B power n? It's just you apply B n times. You make B, 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 B apply on F. What is B power 0? Because I start at 0. What is B power 0? The guy I have just introduced here. The identity, like for numbers, anything power 0 is 1. Okay, Vic, I know 0 power 0. I don't want to hear about it. But if B is 0, you probably don't have to, this formula is not correct for B. That's true. No, it's correct if you take this convention. If B is 0, okay, if B is 0, you have 1 minus 0, it's 1. So I need this convention for any B. Even for the 0, otherwise I have a problem.
That number, 1 minus B to the power?
Minus 1, sorry. The inverse. So in fact, it's not completely trivial because what it says that this operator has no kernel, so it's invertible, has a trivial kernel, it's invertible, and its inverse is equal to this guy. But essentially, it's the same proof as what you do here. Yeah. Yes. There is even I think the norm of 1 minus B minus 1 is probably, I'm not completely sure. It's probably smaller than 1 minus norm of B. Theta, can you confirm that this is correct? I think so. In the Neumann series, I think, I'm not sure, but yeah, it's bounded. Please check. I'm not 100% sure. I don't remember. Oh, yes, I wrote it. Sorry. So 1 minus B norm minus 1 is smaller than 1 minus the norm of B, everything power minus 1. So this is correct. So yes, this sum, it means this infinite sum is convergent. And in fact, it's even convergent in norm. We have seen 3 types of convergences: uniform, strong, and weak. In norm means it's the same as uniform. So this convergence is the best one. So this Neumann series, as this first small inequality for numbers, is very useful. But the condition in order to apply it is really you need to have a norm of B strictly smaller than 1. Otherwise, like for numbers, we know we cannot do it. Okay. I can now do a rather simple section about special classes of bounded linears. What do I mean by this? There are families. So we have some families of bounded operators which share the same properties. So we put them together. And one you probably know for matrices is the notion of Hermitian. But this is the extension. So B in B of H is self-adjoint or Hermitian. We use both. Is self-adjoint or Hermitian if B star is equal to B. And I introduced everything. B star is the adjoint, and so it's called self-adjoint if B star is equal to B, which means that BFG is the same as FBG. All right. I'm not on purpose, I'm not using symmetric. If we deal only with matrices, we can use the word symmetric. But it has, in this framework, symmetric has a slightly different meaning. So I don't use symmetric for now. Just be careful about this. The two official words are Hermitian or self-adjoint. It's not wrong to use symmetric, but we have to be a little bit careful. I will come back to this when I deal with unbounded operators. Okay, let's come back to our favorite example. Multiplication operator. Oh, for matrices, it's clear. Hermitian, you know what it is. It means a transpose complex conjugation. Complex conjugate is the matrix itself. Right? So you know this for matrices. Now for multiplication operator. What does it mean? I use the same notation as before. This multiplication operator. Can you guess when this operator is self-adjoint? So it means when I have such an equality for M. So let's check. M I on F G. What is this? Remember, in L2 of R, this is an integral over R M phi F evaluated at X, G of X, X, but there is a complex conjugation on one term. The scalar product has a complex conjugation. So I take this complex conjugation on the first term. Yes, here. And what is this? This is the integral on R. Now I know what is this. This is phi of X, F of X, everything complex conjugation, P of X dx. Right? That's the definition. Now, I want this. This is what I want to have. That this is F. I want to know what is the condition such that M phi is self-adjoint. So I impose for M phi to be self-adjoint. I impose this. I want to know What is the condition on phi? Can you guess what is the condition on phi?
The same as taking the conjugate on the other function.
Yes, I guess it's correct. So now let me write what is this. By definition, this is the integral on R, f of x, m phi g x x, and complex conjugation on the first argument always, which means this is integral on R, g of x, phi of x, f of x, dx. No, sorry, I missed. This is f of x, g of x. So what do you observe? What do you observe? Phi has to be real. If this number is equal to this number, then we have an equality. So it implies that phi of x complex conjugate has to be equal to phi of x. I could write almost everywhere, but I took phi continuous. So no problem. Almost everywhere you can forget it. If you take phi in L infinity, you can change phi at a few points. So I can just take it almost everywhere. Let's say almost everywhere, or for almost every x in R. But now I need to say if phi is in L infinity of R. We have seen what it is. If you take it continuous and bounded, then you don't need it almost everywhere because the function is continuous, so you cannot change it at a few points. So for what is the conclusion? For multiplication operator, being self-adjoint means the function is real valued. So I can now summary of this example. M phi is self-adjoint if and only if phi is a real function, is a real function. So it means it takes value in R almost everywhere. This is not it. All right. So this is quite simple. So we know what is self-adjoint. Another family or another class of function is made of projections. So second definition, and I'm going to use a slightly different letter. I'm using P. But if you don't like P, you can also call it B. P, belonging to B of H, is a projection if, this is a definition, P square is equal to P adjoint. So what does it mean? What is P square? Remember, P square is P, and then you apply P again. So it means you apply P a first time, and then a second time is just the same as doing it only once. And the adjoint, we know it. This is a definition of a projection. Why is it useful? Simply because, okay. So this is the end of the definition, but a remark. And this is a nice remark. There is a one-to-one correspondence between two things. One-to-one correspondence means there is a bijective relation between two things. So there exists a bijective, so one-to-one bijective relation or bijective correspondence, bijective correspondence between between projections and closed subspace. Of H. I recall what is a closed subspace at the beginning. So let's first think in Rn. We are in R3. What is a projection in R3? No. Take a point in 3 coordinates and just send it to the floor. So take any object and send it to the floor. This is a projection because once it is on the floor, if you do it a second time, it just stays. Or another projection would be push it on this side, on the wall. Once you are here, you cannot do it a second time, or if you do it a second time, you just stay at the same place. So you have, in fact, 3 natural orthogonal projection, which is 1, 2, and 3. Okay. And what is a floor? What is this wall? These are closed subspaces. This is a 2-dimensional subspace. This is a 2-dimensional subspace. This is also a 2-dimensional subspace. In fact, I could also send on a line. It would be a projection to a line going through 0. But so it means there exists a one-to-one correspondence or bijective correspondence between projection and closed subspace. It means P applied to H, which is, this notation is a set of PF for any F in H. This is, you can think as a definition. I just take everything is a closed subspace of H. And conversely, if M is a closed subspace, the closed subspace of H, there exists a unique projection P such that PH is equal to M. This is a one-to-one correspondence. Whenever you have a projection, its image is a subspace, closed subspace, or whenever you have a closed subspace, there exists a P which satisfies this. I'm cheating a little bit. No. I should call it, if I want to be very precise, I should call it orthogonal projection. But usually we forget this word because in this context, it's always orthogonal. In other contexts, sometimes we forget this second condition. We just ask P square is P, and we call this a projection. And whenever we have also equal to P star, we call it orthogonal. But it depends on the context. In the context of Hilbert spaces, we always assume that it's an orthogonal one, and we forget to say orthogonal. So just be careful. If ever you see just these this condition, be careful. Probably it means we don't assume this one. In this case, I should call it projection. And if we have the P star as well, I should call it orthogonal projection. But it depends on the context. Yeah?
Does it change if you use complex instead of real?
Yes, for First, in a real Hilbert space, I don't have this notion of adjoint. So I don't have this notion of orthogonality. We have to be careful. Many things are true also for real vector space, but we need to check at every step that we are not saying something which is not true. So most of the things are true in real case, but we have to be careful. Again, because of this problem, all polynomials do not have a root in R, but in C. But yeah, it's also possible to develop the theory in real vector space. Surprisingly, it's more complicated. It's easier in C than in R. Be careful about one thing. If P and Q are projections, what about the product? PQ, is it a projection? Does it satisfy this? No, not in general. It's not a projection in general. And you can check. In general, I just do it, PQ adjoint. By what we have seen, this is Q adjoint, P adjoint. Now, if both are projections, this is QP, but there is no reason, and there is no reason why this one should be equal to PQ. In general, nobody says that this is true.
Push something to the wall and then the flow is the same as the flow and then the wall, right?
I'm pretty sure you can find some counterexample. Be careful about this. I'm not saying sometimes it's true, sometimes not. But there is no reason from the definition why this should be true. Be careful with intuition. Sometimes it works, sometimes not. It's useful to feel and to guess, but then you have to prove it. A guess is not a proof. There is an exercise. If you want to do something about projection, there is an exercise in the notes that you can do. And let me state one theorem. I could have mentioned this earlier, but now it's a good time to do it. If P is a projection, what about 1 minus P? 1, we have seen it before, doing nothing, or just identity. Is this a projection? Check. It is a projection. If you take the adjoint, it gives you the same. If you took it twice, if you take it twice, it gives you the same. It is a projection. But it has a big consequence. This implies that H, let's say, for any F in H, set F1 is equal to PH, to PF, sorry. Then there exists a F2 in H such that F1 plus F2 is F1 scalar product with F2 is 0. Somebody has used this in a report before, but it was not completely fair to use it too early. What does it say? It says that for any f, take an orthogonal projection. There exists somebody which is perpendicular, such that f can be decomposed into f1 plus something which is perpendicular to f1, which is nothing but, in usual geometry, you know it, you have a vector. So take a line, you have one vector like this. You can decompose it according to f1. So this is f1 like this, and f2 like this. This is nothing but the generalization in arbitrary dimension, and this dimension can be infinite. So this is called the orthogonal, yeah, it's about orthogonality. So we have already seen two classes, self-adjoint projection. What is the next one is unitary. And I use still a different letter. U belonging to B of H is unitary if U star is equal to U minus 1. So it means the adjoint always exists, but it means this U is invertible and its inverse is equal to U star. By the way, this is equivalent to U star is equal to 1 and U star U is equal to 1. Be careful, you cannot only assume one condition. In linear algebra, you have probably seen that if two elements satisfy, if A times B is 1, it means that B is the inverse of A. But when it's infinite dimensional, you need to check two conditions. You cannot check only one. So be careful about this. So we say that it's unitary in this case. Unitary transformation or unitary operators have good properties. So let me do a picture of a unitary transformation. Again, we have H on a U. First, it means if U is unitary, it means the range is everything. So the yellow part is everything. But what about if I take two elements here and compute the scalar product? And if I take the image here, UF scalar product with UG, what can you say about this, these two numbers? So this is a scalar product about two elements here. You have the UF, UG here. Can you say something about this? Kato-san, what can I say?
They both lie on two subspaces.
Also, not always you, somebody else. These two numbers are equal. Why can you see it? Just use a property. This guy is nothing but I can put the adjoint here, U star, UF, G, and by definition, this product, it is this one, is identity. So it means a unitary operator preserves the scalar product. So you have two vectors. You can, in finite dimension, you can think about the scalar product as related to the angle between the two vectors. You apply U, you preserve this angle. And it preserves the norm. The same, you can check that UF is the same as the norm of F. Remember, the norm is nothing but a scalar product of the element with itself. So a unitary transformation preserves angles or scalar product and preserves the norm. So it's very useful. The unit transformation, it just, you change your point of view, but you preserve the angle or scalar product and you preserve the norm. Okay, so this is very, when you have a unitary transformation or a unitary operator, it's very good. Now you're not always so lucky. Definition, V belonging to B of H is an isometry if V star V is 1. Oh, it's very close. Before I had written U star U is 1, but I had written also second condition. Now I impose only 1. But please observe that it implies that VF, VG is the same as FG, and the same norm of VF is the norm of F. So what is the difference? Can you guess what is the difference between these two things? A unitary, which is the picture we have just seen here, and an isometry. How should I modify this picture? There is a small difference.
There's no other arrow. There's no other arrow because there's only one condition.
Yeah, but okay, you're right. There is no inverse. The image, I don't have to have the image everywhere. I can have this part. What is this part? This is range of V orthogonal. So what is the difference? Here, the image was everything. And it was visible because it was invertible. Here, the second case, the isometry, I'm not saying that it's invertible. And usually it's not. If it is invertible, it means it's unitary. It means it takes this part and send it to this, but maybe you have, or probably you have one part which is orthogonal. And there is no contradiction. If you take two vectors here, after the transformation, you again preserve the angle. Simply, you do not touch this part. This is true again in finite dimension. If everything is finite dimensional, you are in the unitary case. This is an isometry. And I think that I put an exercise on isometries as well. And there is a third guy of the same type, W in B of H is a partial isometry. This is the last one. Is a partial isometry if W star W, of course, I cannot write identity because if I write identity, I'm back to isometry, is P, which is a projection. So this product is a projection. So how should I modify again this feature? This is H. H. The range is going to be the yellow part. This is orthogonal to the range. But it turned out that what is the kernel of an isometry? The set of elements which are sent to 0. If it preserves the norm, the only element which is sent to 0 has to be 0 itself. Now, in this case, for partial isometry, the kernel, this is the kernel of W, is precisely P os 1 minus P applied to H. It is this projection on a certain. So this part here is equal to PH. It's a subspace. Then if you take two elements here, they are sent on this one and it preserves the angle and the norm. But if you take an element here, it is sent to 0. And in addition, this range is not everywhere, but you may have something which is also going. Again, if we are in finite dimension, there is no such things. I don't remember if I put also an exercise on partial isometries, but yeah, if you can see the difference between a unitary element, an isometry, which they all preserve the angles, but here it's true for any element of H on the image. Here, you may have a kernel, and if you take something which is not in the kernel, you preserve the angle. So unitary isometry, partial isometry. And if I do a last picture about this, how should you represent this unitary isometry? And partial isometry. Why? Observe that P can be identity, P can be 1. There is no contradiction, 1 is a projection. So it means the set of partial isometries contains the set of isometries. And the set of isometries, you had only one condition, but if two conditions are satisfied, you have a unitary element. So this is the way it's generalized. All right, any question or remark? Yes.
So if you have any element on Earth, I would assume the zero element in the right-hand side is the range of W orthogonal.
So all these, so somewhere we have the 0 element. This is sent to the 0.
I would assume the opposite. The zero element.
In fact, the 0 is, in fact, it's in every subspace. The 0 element is, I should represent it here and I should represent it here. Then there is no contradiction. Yeah, the 0 is like in this subspace, and in this one, the intersection is a line, but both go through 0, the point 0. You know, this picture is always misleading. We are speaking about vector space. So in every direction, I should be able to go to infinity because I can just multiply by a scalar. So it's not a perfect image. But try to represent a space which is of dimension infinity. It's not so easy. All right. So we have seen a couple of families of operators: self-adjoint, projections, unitary, isometry, partial isometry. And they play a big role in quantum mechanics. You will probably see them again in a good course on quantum mechanics. Now, finite rank operator. And they are essentially matrices. I will try to convince you. So take Fj and Gj, j from 1 up to n finite number inside. So what do I mean? I just mean I take two families of vectors, and one family is called F, the other one, they are called G. That's it. And set and define the operator. A, I call it A applied to F. I take F inside H. So let me give you a definition. It's a sum of which order? What is this? And I do a sum j from 1. What is this? Look, I take F, I take a scalar product with Gj. This is just a number. Once I have done this scalar product, this is just a complex number. And I multiply Fj by this number. So it means I do a finite linear combination of the Fj. I have F1, which I multiply by a number, plus F2, that I multiply by a different number, plus F3, that I multiply by a different number. So it's only n vectors. And this scalar product depends on the other family. So just exercise. Check that A belongs to B of H. This is a bounded linear operator. Why is it linear? Because if you take, I should not call it F1 and F2. If you take F plus lambda F prime, it's linear, you can see. So this is an exercise. Check that this and compute the norm of A, or at least upper bound on this norm. This is an exercise you can do. Why is it close to matrices? Can you see why I can consider this almost as a matrix?
The scalar product is almost a projection.
No. This is not the reason. Somebody else. Look, if F is perpendicular to this finite family of vector Gj. So you have this vector space generated by these n vectors. If F is perpendicular, this is 0. Because the scalar, as soon as F is perpendicular to these n vectors, you have 0. So it means only the vector space generated by these n vectors is important. And the same for the range. Look, you are doing a finite linear combination of this Fj. So it means everything is in the subspace generated by these n vectors. So it means it's F should be inside a space of dimension n, at most n generated by these n vectors, and the image is again at most of dimension n. This is a matrix. So you can think about it. A is not trivial. Not trivial means not 0 on vector of F1 up to Fn and has range in vector of G. Oh, no, sorry, the opposite. Sorry. This is G1 up to G. G1 up to N and F1 up to Fn. See, And this is not really different from a matrix. It takes, it can be of smaller dimension than n because I have not assumed that these n vectors are linearly independent. So some of them could be linearly dependent. But it takes something in a vector space of dimension at most n and send it to a vector space of dimension at most n. Otherwise, it's trivial. It's almost it's a matrix. So this is called a finite rank operator. A is called a finite rank operator. This is the official name. So let me do another picture, even if it is just a picture. B of H. You have a small thing, small part of B of H. This is finite rank. Finite rank operator. And now you can wonder what happens if you try to take linear combination up to infinity, but you have to be careful what means taking linear combination up to infinity. So let me give you a precise, and this is going to be this blue part. So the question which is not precise is what happens when n goes to infinity? But I have to be more precise. Definition. Let's see, B in B of H is a compact, this is the name, is a compact operator. And you should think about this as a blue region. I'm going to call it compact operators. What could be the definition? I want to take n going to infinity, but you can imagine it's not so easy. So it's a compact operator if for any epsilon bigger than 0, there exists a finite rank operator A such that the difference is smaller than epsilon. B minus E norm is smaller equal to epsilon. So it means what I call a compact operator can be approximated as precisely as you want by a matrix. So this is a natural extension of a matrix. It's up to an epsilon, it's a finite dimensional matrix, but this epsilon is important because it doesn't mean this B is a matrix, but it can be approximated by a matrix. This is a notion. And how do we denote this set of compact operator? There is a notation for this. We write K of H for this set of all compact. The set of all compact operators. And this picture is correct in the sense that it's still a small set inside B of H. So this is much bigger, but still here you have essentially matrices. The closure or it's a kind of density. Inside the set of compact operators, the finite rank are dense. Okay. the finite rank operators are dense in K of H, exactly because of what I have written here. It's the definition of density, right? This is an important notion, the set of compact operators. Let me just state a few properties. Which are easy to check. Properties. If B is compact in the sense I mentioned, its adjoint is also compact. Probably this is something you can do in the following way. Take a finite rank A and check that its adjoint, we know the definition of an adjoint, its adjoint is also finite rank. And then when you approximate the adjoint of B, you are going to use the family, the same operator, but adjoint. Can you guess if B is compact and now C is any bounded operator? Then what about the product? Then either BC or CB, they are not the same. When you, like for matrices, if you take in this order or in this order, there is no reason for them to be equal. Can you guess something about this? They are bounded. This is true, but you can say more. B can be approximated by matrices. You multiply by a bounded operator. These are also compact. Then are also compact. It's a nice exercise. If you want to understand what means this, try to make this exercise. Check that this is true. And it has a name. You remember from the first chapter, whenever something is attracting. Yes, correct. K of H is an ideal in B of H. It means it attracts. You multiply one element of K of H with one element of B of H, the product in both order is compact, right? Okay, there is one more property, but I don't need to record it. One good, let me state one third property. K of H improves convergences. I will make it more precise. What do I mean by this? If we consider Fn a sequence in H with weak limits. This last property is not so important. If you don't like it, just forget it. I consider a sequence which converge weakly, which means it converges only in scalar product. Then if most of the time we use a letter K for compact operator because it's natural. K is a compact operator instead of B. Then K in K of H, one has. Now I consider KFN. It's again a family of vectors, but it converges to KF infinity. Now, if you understand that it improves convergence, it means it's converge strongly. KFN converge, and n goes to infinity strongly. So it's improved in this sense. Something which was converging only in scalar product, now it converges in norm. And you have something similar. So you have two properties like this. But I state only one. So compact operators are useful. All right, I have just a few more minutes. I just want to sketch. I was not planning to spend a long time on it. But is there any question? So we have seen a couple of families: self-adjoint, projections, unitary, isometry, partial isometry, finite rank, and compact. If you feel a little bit these families, it's very good. The next section, which I just want to sketch, it's about vector valued functions and operator valued functions. What do I mean by this? I consider phi. So what kind of function you know? You know a function from an interval to R, maybe to Rn, to Cn. But why about a function with value in a Hilbert space? It means phi of x is not just a complex number, is an element of H for any x inside AB. It's, you know, it's like you have the interval, and at every point of the interval, instead of having just a vector would be a if you think about finite dimension, take the interval AB. A usual function is you associate a number, a real number. Now, a vector valued function, you associate a vector. At every point, you associate a vector, all right? At this point, and it evolves when you move on AB. Then, instead of having a vector, you can think about this as an element of the Hilbert space. Yes, Cn was the first example of finite dimensional Hilbert space. So you can indeed think about this inside C2. But now we can make it more general. It can be a function because one Hilbert space is made of function, the L2. You have a... So what means continuous in this case? What means this function is continuous? And we have two notions of continuity. Phi from AB to H is strongly continuous because we have two notions of convergence. It's strongly continuous on AB if take phi of x plus a small epsilon minus phi at x. This is what we do when we consider continuity. This is an element of a Hilbert space. This is another element. I take the norm and I impose that this goes to 0 when epsilon goes to 0. This is a natural notion of continuity. Or phi. Phi is weakly differentiable, weakly continuous. Can you write the definition? Instead of this is a strong notion of convergence. Yes, the scalar product, if for any G in H, now scalar product of G with phi of X plus epsilon, this is just a number, minus phi of X. So I take in the scalar product. This is just a number. Goes to 0. It goes to 0 as epsilon goes to 0. This is a weak continuity. We have two notions of convergence, the strong one and the weak one. So we have two notions of continuity. And the same for differentiability. Let me just write one of them, still in the definition. Phi is strongly differentiable. I mean, everything is quite natural. If there exists a function phi prime from AB to H, such that, so what do I have to write for differentiability? 1 over epsilon phi of X plus epsilon minus phi of X. This is how we define the derivative minus the derivative. When I take this, goes to 0. This is notion of derivative. It's going to be what we call the derivative. So if there exists a function, you are going to call it the derivative, but it's another function, such that when you take phi of X plus epsilon minus phi of X, but you divide by epsilon, it's approaching phi prime of X. So this goes to 0 as epsilon goes to 0. This is a natural notion of differentiability. And you can, I let you write what means weakly differentiable. You just put a scalar product instead of a no. This is for vector valued function. Just be careful about one thing. If phi and psi are both from AB to H, can you make a sense to phi times psi, the product of two functions? Can you make a sense to this? No.
Isn't it an idea? Oh.
Please don't. You're not the only one. We have 20 students in the classroom. Can I give a meaning to this? Why yes or why no? So if I can give a meaning to this, it means when I evaluate it at X, it should be equal to phi of X, psi of X. All right, this would be the natural definition of a product. What is this? This is an element of H. This is an element of H. Can you multiply two elements of H? No, you can take a scalar product, but it doesn't give you an element of H. It just gives you a number. So this is not well defined. So be careful. This has no product. Function from AB to H has no product. So it's not an algebra, has no product. Just be careful about this. I will stop after one more sentence. This is your homework. What about now functions psi, take a capital letter, from AB to B of H? So think about a function having values in the set of matrices. Think about this. If it is finite dimensional, this is a set of matrices. So at every point, you have a matrix. You can define the notion of continuity of this function. You can define three notions of continuity, because on B of H, we have seen the notion of uniform convergence, strong convergence, and weak convergence. So three notions of continuity, three notions of differentiability. What about the product? If I take two such functions, can I define a product? Yes, because on B of H, you can multiply. This is meaningful to have one bounded operator times a bounded operator. So on B of H, for function from AB to B of H, you can define the same thing and you have a product. It's an algebra, just for information. I will quickly review this at the beginning of next week, and then we start unbounded operators. It's already written in the notes. If you are curious, you can look at it. Okay, thank you. If you have any question, you can interrupt me.